Hello student. Let's begin Module 11. Lessons 11 and 12 will cover Chapter 7 of our textbook, Power Series Method. Here's an overview. Let's begin with a general form of a linear ODE with variable coefficients, like this, homogeneous case, or like that, non-homogeneous case. Either way, in any case, let's assume all the functions here are analytic. I mean all the functions. Y of t, f of t, a0, a1, a2, all the way over to an. Let's assume everything is analytic. Analytic. What do you mean by that, by the way? In case you don't remember, here's a reminder from Calculus 2. A real function is said to be analytic around t0 if it can be written as a power series centered at t0 like this. The power series should be valid in a certain open interval centered at t0, which we call the interval of convergence. Now please remind yourself that coefficient sequence Cn can be written in terms of the derivative, nth derivative of y evaluated at t0 over n factorial. Does everybody remember this? Is this familiar to everybody? This formula, I mean. What is it called? Taylor's theorem, or Taylor's formula, or Taylor's series. There are many names, but in any case, it's associated to Taylor. I hope everybody remembers that. If you don't, it's going to be a good idea to review Calculus 2 materials. You can go back to Calculus 2 textbook. And also, our textbook author did a relatively good job explaining necessary concepts rather briefly in our textbook. And I did my part reviewing that in section 2 of this notebook. Here, let's have a really brief review. Let's begin with this power series expansion here. And it turns out there is a non-negative extended real number capital R, which we call the radius of convergence, such that this power series expression converges absolutely when the distance between t and t0 is less than the capital R, and diverges when the distance is greater than the same capital R. That number is called the radius of convergence. How do you calculate it? Here are a couple of computation formulae. The first limit is coming from the ratio test. It's a reciprocal of the ratio test. And the second is coming from the root test. Again, it's a reciprocal. Of course, in order to have in order to use these as computational formulae, the limits must exist. But please remember this: capital R always exists. Whether the limits exist or not is a different issue. If these limits do not exist, then that means you cannot use these formulas to calculate capital R. That's all there is. That does not mean this capital R does not exist. The radius of convergence always exists because it is defined not through these limits, but using the limit superior, to tell the truth. But then again, this is Calculus 2, not Calculus 2, this is Analysis 2 topic. So let's not go too deeply into that. The point I was trying to make is the capital R, the radius of convergence, always exists, whether these limits exist or not. Also, this capital R is an extended real number. It can be infinity. What if it is infinity in that case? This is never true because nothing is greater than infinity. And this is always true. Everything is less than infinity. So this blue condition is always true for all t. Consequently, the power series converges absolutely for all t. Now, the other end of the extreme is r equal to 0. In that case, we have to have divergence here because everything is greater than 0 except, of course, 0 itself. In that case, we have equal to 0, and that's the only way to avoid divergence. Then what do you mean by t minus t0 is equal to 0? That means t is equal to t0, in which case this part, t minus t0, is just 0, so 0 to the nth power. They all disappear for n equals to 1, 2, 3, 4, everything. And the only thing that we have is y of t0 equal to c0, because only the n equal to 0 case, very first term, the constant term, remains. And this is not helping. It's not a series expression, and it doesn't really tell you anything about a y of t other than t equal to t0, so it's not helping. In this case, y of t is not analytic. In order to have an analytic, in order to have in order to satisfy the condition for analytic, we have to have an open interval centered at t0. Okay, if it is just t0 only, then it's not an open interval, so no, not analytic. So that's the condition we're going to pose to all these functions here. So for example, f of t is analytic in a certain radius of convergence, say RF, and then A0 is analytic with radius of convergence R0, and then this one has radius of convergence R1, and so on and so forth. And what we are going to take is the smallest of them all, and then take that as my radius of convergence, and within that interval, I'm going to get a unique solution like this in a power series form. That is basically the theoretical foundation of the power series method. And that's why I named it the fundamental theorem, because it gives you the foundation. It goes like this, given any, let's see, this expression, by the way, is not exactly the same as the original here, but please note that these two are equivalent, because this expression here is a linear ODE with variable coefficients, but it has order n, so this function, leading coefficient function, is not identically 0, so you can divide by this an, then you're going to get this expression. So yes, this expression is equivalent to previous. Now in this case, we can consider the radius of convergence for all these functions, g, b0, b1, all the way over to bn minus 1. And then we're going to take the smallest of all. Let's call that capital R. And within that radius of convergence, we're going to have a unique solution, y of t, in a power series form like this. That's the fundamental theorem. Now, this fundamental theorem has two parts, existence and uniqueness. The solution exists in power series form, so that justifies our effort to find out a solution of this form. You see, this expression exists, so the direction we are taking to find this kind of form is valid. If it doesn't exist, then it's not valid, it's pointless. Second, the solution is unique. So if you successfully find an expression like this as a solution, then that is the solution, the one and only solution. Of course, the proof of the fundamental theorem is too deep, so we are not going to go there. But just remember, the theoretical foundation here gives you the validity of whatever method that we are going to be learning from now on. And that method will start from section 3, but we need one more review from section 2 here. I'm going to leave nearly everything to students and an optional video, but let's take this one, index shifting. This may be new to a lot of students. As a matter of fact, this is one topic here that I do not cover in Calculus 2. The others I cover, but this one I don't. And it goes like this. Compare first and the third series here, or blue series here and the red series there. My claim is those two are the same. They may look different, but they're the same. And this one is expanded in terms of n plus first power, but this one is going from nth power, so they may look different, but the starting points are different also. So they'll turn out to be the same. As a matter of fact, you can check. Let's see. I begin from n equal to 0, so plug in 0 there. 0 plus 1 is 1, and then t to the 0.1, so first power. And then next, n equals to 1, so 1 plus 1 is 2, times t to the 1 plus 1, second power. And then n equals 2, so 2 plus 1 to 3, t to the third power, and so on. That's what we get. Now what about this red series here? Do we get the same thing here? Yes, indeed. And please check. We begin from n equals to 1. So instead of starting from 0, I have to start from 1s. So n equals to 1, n equals to 1. So we have this. Next, n is 2. So 2 times t to the second power, we get that, and so on. You see, they're the same. Now, how do you get the red series from the blue series to begin with? Here's an idea. We take appropriate change of variable, and we want to change this n plus first power into nth power. So let's take this change of variable. M is n plus 1, and consequently n is m minus 1. You see this change of variable. And then when m begins from 0, m will begin from 1 because you see n is m minus 1. Oops. So n is equal to 0 means m minus 1 is equal to 0. And therefore m is equal to 1. And that's how you get this black series. And then change the character m to n, then you're going to get this red series. You see? And this kind of explanation is rock solid. Great, but then again, it's too cumbersome because we have to introduce another character. So let's take a shortcut. And let's look at the next expression here. And here, I want n plus first power to nth power. Okay, so one way to do that is to change this n to n minus 1 like this. Then I'm going to get n minus 1 plus 1, so that's the nth power. So we get what we want. And always begin from the power. Now, I changed n to n minus 1, so we'll have to do the same thing for everything here. This n becomes n minus 1. And this n also becomes n minus 1. Alright? And then simplify. N minus 1 plus 1 is n. Same here. And n minus 1 is equal to 0. We get n equals to 1. So the second method is a little bit easier. And you can get used to this rather quickly. So frequently you change n to n minus 1 or n minus 2, n minus 3 like that, or vice versa. Change n to n plus 1 or n plus 2 or n plus 3 like those, depending upon what's your target. You see, I'm beginning from n plus 1 to n, then I need n minus 1. If I begin from n plus 3 to n, then I need, okay, I stop here, think about it. Here's an example problem, index shifting example problem. And this too is actually an elementary example. Okay, and let me expand the font a little bit further even. Okay. Okay, here, my target is to get nth power. What substitution, what replacement do you have to do it to this part to get nth power in the end? What? So look at the power. Did I get nth power? N minus 1 plus 1. Did I get it? Yes? Yes, I did get nth power. So that's how you do it. Okay, all right, that's a strategy. I'm going to replace n by n minus 1. So this one, this n, and then this n, and this n. and then some simplification, and that's about it. This n minus first power, let's keep it. N minus 1 plus 1, that's going to be just nth power. N minus 1 plus 1, that's going to be nth power. Here n minus 1 is equal to 0. You're going to get n equals 1. And there you go. I can keep this one as is, or I can change it to nth power and then bring extra negative outside. Either way, it'll work out. So this kind of thing is called index shifting, and this may be a bit new to everybody. Probably new to everybody, I think. So I thought it was worthy of our class time. Otherwise, entire section 2 is review, so I'll just skip here and dump it over to an optional video. Let's meet again with section 3.